Hello everyone, and welcome to today's chem lesson. We're continuing our discussion of nuclear chem today by talking a little bit more about the way radioactive particles decay, specifically half-life. Now, half-life is the way that we track how long it has been since something started to decay, or how much there is remaining of what was decaying. Half-life is the amount of time it takes for half of a radioactive substance to have decayed. That means if we have 100 grams of a radioactive substance, after one half-life, it will become 50 grams radioactive substance and 50 grams unradioactive. After another half-life, same amount of time, it will become 25 grams. Each half-life tracks how long it takes for half of the mass of that substance to decay. Now, why is it a different amount every time, right? If this is 10 years, why does it take 10 years to lose 50 grams and then 10 years to lose another 25 grams? That's because what we're tracking here is the probability. And the probability doesn't change, right? There's always a 1 in whatever chance that an atom decays. And the more atoms there are, the more are going to decay. The fewer atoms there are, the fewer atoms are going to decay. For us, in a Regents chemistry course, we're actually not looking at any difficult or troubling math here. We're looking at putting a number in the calculator and putting divided by 2 as many times as we need to before we get to our answer. Alright, now what does that mean? Mr. M, what are you talking about? Let's look at this problem. An unstable isotope of carbon has a half-life of exactly 2 years. How much time must pass before 1.25 grams of a 20-gram sample remain? Sure, okay, that's definitely a question. Alright, we start with 20 grams. After one half-life, after 2 years, so that's what it tells me in the problem, we have 10 grams left. Okay, so 2 years have passed. We still haven't reached our target. Another 2 years go by, it gets cut in half again. Right now we've got 5 grams left. Another 2 years go by. We have 2.5 grams left. Another 2 years go by. We have 1.25 grams left, and all of a sudden, we've reached our target. So how long did that take? That took 1, 2, 3, 4 half-lives. Right, 4 half-lives. Or 8 years, right? Because each half-life is 2 years. Since they asked us how much time has passed, we're going to pick 8 years as our answer. Sometimes the question is how many half-lives have gone by, and then it's 4 half-lives. The half-life for a lot of different things are listed out on table N, right? We talked about that a little bit last time. How table N gives us these radioisotopes, their decay modes, and their half-lives. Some half-lives are very, very long, like thousands upon thousands of years. Some half-lives are much shorter, even to the point of seconds. Different half-lives for different substances give those substances different benefits. Right? We can talk about, or we will talk about those in a little bit actually. But first, let's look at a practice question. If 2 grams of a 128 gram sample remain after 48 years, what is the half-life of the sample? how do we answer this? First, we say if we had 128 to start with, and we ended at 2, right, we're going to cut this in half until we reach 2. 64, 32, 16, 8, 4, 2. Right? Cutting it in half each time. Each one of these arrows represents one half-life. So we have 1, 2, 3, 4, 5, 6 half-lives. And we know that that takes 48 years. If 6 half-lives takes 48 years, that means each one of those half-lives, this is 8 years each. So the half-life of that thing is an 8-year half-life. Right, just cutting that number in half over and over and over again and thinking about it. Certain radioisotopes, right, certain radioactive things have uses because we know about their half-lives. Right, the two most common that we talk about the most in science are uranium-238 and carbon-14. These are used in the dating of things, figuring out how old something is by comparing the amount of the radioisotope, the amount of the radioactive thing, to the amount of non-radioactive thing. Sometimes these pop up as questions on the regions, but really what I like to point out here is that radioactivity and radioactive isotopes are used for more than just war. Right? There's more use for radioactive things than just looking at how can we make a very big explosive bomb. Right? Everyone gets so worried and so scared of radioactive things because they get hyped up in movies and in shows and in history. Right? We've seen the devastation of a nuclear bomb. That we don't really stop to consider all of the ways that radioactive things and radioactive isotopes can actually are used to help the human race. I'm going to leave you to think on that for a little while. I've got one more video left in this unit, one more thing left to talk about, and that's fission and fusion. But just like always, that's not a today thing, that's a next time thing. And so, I'll see you then. And for now, just go out and have a fantastic